So I'm Kevin Maschhoff from BAE Systems. I will be talking about a project that we just initiated, an instrument incubator called SToRM SAR, for which I'm the TI. Marty Riva, also of BAE Systems, is a co-investigator, and Professor Chandrasekhar at Colorado State University is also a co-investigator in this activity. And we began this in April of this year. Next slide, please. The challenge that we're addressing with SToRM SAR is the ability to observe fine spatial structure in precipitation fields from space. The need to do this is shown in this chart, where we're looking at reflectivity on the left and classification of hydrometeors, rain, ice, etc., based on their phase. And as you can see, there's a fair amount of structure at the kilometer scale. These measurements were taken by a ground-based radar. The challenge then is to see if we can find a way to measure this sort of spatial resolving, or measure with this sort of spatial resolving power for intense convective storms from space. Next chart, please. You've seen this picture before. The GPM main observatory has a dual band precipitation radar working at KU and at KA bands. They've been able to accomplish significant scientifically relevant and helpful observations with this platform over the years. It's an expensive project, however, relative to, I guess, our current understanding of what one might be able to do, implement with microsatellites. And the specific technical challenge with respect to convective storm observations from space, particularly mid-latitude storms, is that the spatial resolving power of this approach is diffraction limited at several kilometers, close to 5 kilometers spatial resolution in KA band, which is the primary band used for the more intense, more absorptive storms. You can see in the lower right panel the relative scale of this antenna. So the problem is, how would one actually go to a much larger antenna in order to obtain the higher spatial resolution using the real aperture method? There are certainly other design implementations than using a large phased array radar, large area reflectors, and so forth that could be employed in a different design concept. But the underlying problem is that they're all going to be large and therefore costly to develop and deploy in space. So let's go to the next slide, please. So our approach is an interferometric approach employing multiple microsatellites in low Earth orbit. We have here our array, which includes a transmitter satellite and 2 receiver satellites. And it includes the fact that we can time synchronize our observations between the transmitter and each of the 2 receivers when we are processing our interferometric products. So the approach is to actually employ a combination of this cross-track interferometry that's depicted here, as well as some tomography, a layer slicing of the atmosphere by using a spotlight mode way of operating this satellite set. This is a class of multi-static observation, and we would change the line of sight of the receivers and the transmitter as the satellite group is passing over the field in order to implement the spotlight mode way of operating. By this method, we're hoping to obtain high spatial resolution in both the along track as well as the cross-track directions together with more conventional vertical sampling of the precipitation field. Next chart, please. One approach to obtaining higher spatial resolution from space would be to use ever higher frequencies. The attenuation, however, of the beams within a strong convective storm is going to limit you here. Here what we're showing are the attenuation per kilometer at KU and again at KA band, and that there's a rather dramatic difference. And so the challenge is that in order to look at our target science observation, which are intense storms with fine spatial structure, we can't simply go up to higher spatial or higher frequencies to make the diffraction problem simpler. So that's motivated our look at these interferometric multistatic methods. Let's go on to the next chart, please. Part of the advantage here of going to the multistatic methods is that we can use the geometry of separation to help us with our separating out of the information. We basically get two different vantage points with two different separated receivers. These receiver separations on the order of a 10-kilometer or 20-kilometer separations or so. And as a consequence, the difference in range between the two receivers is an important attribute. And it turns out that under the geometric conditions that apply, the difference in range from a scattering center field to each of the two receivers is proportional to the cross-range position. And then in the along track dimension, we're looking at what's called a shallow angle tomography scheme, where we're actually going to be looking at the same set of atmospheric conditions at a different set of angles as we overfly the storm, and by inverting that process, we'll recover spatial dissolving power in the along track direction. That's the vision. This is a new observation concept that we will be doing some ground-based demonstrations on in order to validate its capabilities. Let's go on to the next chart, please. Our approach to doing ground-based validation is to leverage the powerful precipitation radar currently in place in Fort Collins, or just south and east of Fort Collins in Colorado. This is the chill facility that whose radome is shown in the lower right. And our approach will then implement spatially separated receivers, time synchronized using the GPS system. And we will be comparing the results of our observations with the results of a real aperture precipitation radar operated at X-band using the same waveforms that we'll be using. And we'll be developing and verifying the technique using that reference. Actually concludes the presentation.